And now let's move to high energies. This, by the way, it's artist's concept of New Star, which is a satellite that observes gamma rays right now, circling overhead, and it's run out of this building, Fiona Harrison and her team, and it's studying phenomena that emit radiation high energies, like accreting black holes and what have you. The whole field started after World War II with first rockets used to probe things. And so again, the surplus German V2 rockets were used to do the first astronomy from space. And this was a particular experiment with the X-ray detector. They were hoping to detect X-rays from the moon, sun, obviously. And they also did this, at the same time, they discovered first extrasolar X-ray sources. They didn't see the moon. And they also discovered presence of the uniform X-ray background on the sky, which we now know is due to gazillions of quasars and similar things. But that resulted in a Nobel Prize for Riccardo Giacconi, only 40 years later. But it's better late than never. A large number of X-ray missions have been up there since then. Here are some of the more famous or more important ones. The one on top left is was nicknamed Einstein. It was first really serious X-ray satellite that did X-ray maps of the sky and discovered all kinds of sources. Its successor in 1990s was ROSAT, for Röntgen Satellite, German obviously, and that produced a much better X-ray survey of the sky. And that was followed by one of the NASA's great observatories, Chandra, which has essentially resolution like optical telescopes, but in the X-rays. And also can take spectra in X-rays, which are almost like low-resolution spectra in visible light from the ground. And its counterpart from European Space Agency is called XMM, Newton. And you can see they kind of look the same. And this also kind of looks that way. And the reason is they have to have long focal lengths. The long focal lengths are due to the fact that X-rays are really hard to focus. But it's possible, and that's done with so-called grazing incidence mirrors. Now, I think last week somebody asked a good question, or guessed the answer to my question. Why can't we focus gamma rays? We still can't focus gamma rays. For any material to work as a mirror, the spacing between crystal lattice elements, atoms, right, has to be less than the wavelength of that radiation. And typically in metallic crystals or whatever, it's of the order of angstroms. And so once you start getting to wavelengths that are comparable to angstrom or smaller, you're just going to go in between. This is why X-rays are used as X-rays. That's why they see through human body. So you can trick X-rays by tilting your mirror in such a way so that in perspective, the spacing between individual atoms is much smaller than if you were looking at face on. And so then you can get reflection at a very oblique angle. So that means that you have to make parabolic mirrors that are really, really deep because you're bouncing off those edges of the parabola. And because they're coming almost in parallel way, then you can nest a whole bunch of mirrors together. And this is how they're done. This is a set of mirrors for Chandra, which I believe are the most precise mirrors ever made for anything. Forget what precision it is. So it's possible to focus X-rays. Not so much with gamma rays. They're essentially, gamma rays will go through everything, they occasionally interact with something. And so our gamma ray telescopes are really gamma ray detectors, right? The detector itself captures gamma rays in some way, and you measure where it came from or something. The kinds of detectors that are used in X-ray and gamma ray astronomy essentially all started as particle physics detectors. The first ones were proportional counters, which is just like a Geiger counter. You probably know how that works. There is almost evacuated tube with an anode and cathode, and say X-ray comes and knocks out an electron, and so there is a net charge. You can pick it up from gas. Slightly better nuclear physics detectors are scintillation crystals, where there is interaction of a gamma ray with some material, and that creates a little flash of light that you can pick up with sensitive photomultiplier tubes. But more modern ones are sort of like CCDs, only for X-rays or even soft gamma rays. They're made out of strange metallic combination like cadmium, zinc, telluride. And that thing there is the set of 4 of them in the focal plane of new star. So that's how they can actually take pictures once you can please focus this card X-ray a little bit. Another way to go about this is to use Earth's atmosphere as your detector. So you have a high-energy gamma ray, hits some unfortunate atom in the upper atmosphere, splits it, gives it some momentum. You have moving charges, electron and the rest of the ion. Then they knock out other atoms and ionize them and so on. And so they keep dividing the energy. So from one high-energy gamma ray, you can generate a whole bunch of others. And at first, they all have so much momentum that they can move faster than the speed of light in the air, right? And that creates Cherenkov radiation, which is like electromagnetic sonic boom. So you can see flashes of light from high-energy gamma rays in the sky and pick them up, and that's done with big photon bucket mirrors like these.